When it comes to the relationship between functions, arrays, and pointers, for that matter, things get a little tricky. First, the size of operator we use to determine the size of the array. Well, even though the array and the pointer in this example work much the same way, the size of operator only returns the size of the array when you actually apply it to an array variable. Let's check. Ignoring the unused size variable for the moment, we can see that the size of numbers is 12, the number of bytes required to store 3 4-byte integers. But the size of p is only 4. 4 here is not the number of bytes required for one 4-byte integer, but rather the number of bytes required for one address, one pointer to an integer. On a 64-bit machine, this would be 8 bytes. The point is that we have lost some compile time information. The pointer, even though it can do practically everything the array variable can do, it does not carry the same compile time information. Well, when you pass an array to another function, your only choice is to pass it as a pointer. Now, whether we pass the pointer or the actual array, it makes no difference. So what's the problem? Well, this print function has no way of knowing how many integers or elements this pointer points to. Is it 1, 0, 10? Who knows? Of course, we know, but if we embed this knowledge in the print function, we're going to cause a maintenance nightmare, as the main function won't be able to change without also changing the print function. One option is to pass the size as an additional argument. Now, the function expects an additional parameter, and the caller is compelled to provide the size. It's useful to standardize such functions one way or another, either like this, with a pointer and a size, or with a half-open range, as I illustrated before, using 2 pointers. The C++ standard library offers many more algorithms than the C standard library, so as you progress to C++, you may find the use of half-open ranges more beneficial, as that's the C++ convention. Now, I just need to pass the end of the range rather than the size. And we've already seen how this may be implemented quite simply with the for statement. Notice how I'm updating the begin parameter directly. Even though this pointer originated in the main function, the print function has a local copy of this pointer value, so any changes to the pointer itself is local to the print function. Of course, if the print function were to dereference the pointer and assign it a new value, then the main function would be able to witness that change. But what if we wanted to return some information to the caller? Some information about the array. Perhaps the pointer to the largest value. But now we have another issue to deal with. What if the provided range is empty? Well, that's easy enough. If begin equals end, then we know there are no elements to print or scan. We didn't need to check this explicitly before, since the loop condition would simply have been false from the start. But now we need to return a value one way or another. So if begin equals end, then we can simply return a null pointer, an invalid pointer, a pointer with a value of 0. The rest of the function can then assume that there is at least one element in the range. So we need to discover the largest value in the range. Well, we could write another loop, but that would be wasteful. Let's just reuse the loop to avoid the extra scan of the range. We can begin by assuming that the first element has the largest value. Now I have 3 pointers, one pointing to the start or begin of the range, and which will be updated until it reaches the end, another pointing to the end of the range, and a third pointing to the first element, and which I can update if I find a larger value. So after printing the current value, I can dereference both pointers to see whether each successive element is larger. And if so, update the largest pointer to point to the current element. So I'm comparing the values being pointed to, but I'm only actually updating the addresses or pointers themselves. Finally, I can return the result. Okay, let's give this a try. Let's use some more interesting values. And let's get at the return value. Of course, our function is written to safeguard against empty ranges. As the caller, we know that the range is not empty, but we can play it safe and future-proof the code a bit just in case. And now we can safely print out the largest discovered value by dereferencing this pointer. Okay, let's see. And sure enough, 5 is the largest value. Next up, a close cousin of the array, the string literal. In this segment, we need to talk about string literals. String literals are just arrays, but with an interesting property, which is somewhat conventional, but reinforced by the compiler to a degree. Here's your typical C-style string. This is a string literal in the sense that the storage is baked into the executable produced by the compiler, so its storage is ensured and static. You don't need to worry about it. The string variable in this case simply points to where the storage ends up in the address space of the calling process. But we could also treat it as an array. It doesn't make much difference. Now, instead of an array of integers as we had before, we just have an array of characters. Either way, string itself points to the beginning of the string, the sequence of bytes in memory holding the familiar message. Of course, with an array, we can ask for its size. But if we just assume it's a pointer, we can also determine its size, but it's going to take some CPU time. You see, the size of operator returns the constant value known to the compiler before the program begins. The alternative is scanning the string looking for its end. But how would we know where it ends? Well, the compiler again does us a favor and inserts a 0 byte, called a null terminator, at the end of the string literal, at one past the end, specifically if you want to think in terms of a half-open range. So we can write a little loop to count the length of the string by searching for this null terminator. Again, you might devise a dozen ways of doing this. Here's one. First, let's create a length variable, initialized to 0. Then we can scan the string with the for statement and a pointer as the loop variable. we initialize the loop variable to point to the start of the string. We'll continue as long as the pointer doesn't point to the null terminator, and simply increment the pointer to check the next character. As long as the condition holds, we can increment the length. And let's print it out. Okay, let's see. Okay, so that makes sense if you think about it. Remember, the size of operator returns the number of bytes, not elements. The number of bytes of storage required for the string includes the null terminator. But the length of the string is customarily considered to include only the characters that make up the string, the so-called elements of the string. How might this length calculation be implemented differently? Well, consider what you might do if it were a little helper function. The string length function would return the length of the string. Well, now we have a local copy of the pointer, so we don't need to make a copy ourselves to avoid affecting the rest of the program. We then also don't need to use a for statement, alone among the C iteration statements that support embedded declarations. But we still need a counter. But we can use a simpler while loop. So that's the loop condition, while the character being pointed to is not 0, or the null terminator. Of course, the condition of the while statement need only return a true or false value. A non-zero value is enough to keep the loop spinning. So we could simply write this. The only character that would cause this condition to fail is the null terminator, since it alone has a value of 0. We still need to update the string variable for each iteration, but we can use the post increment form right here. That ensures that the condition is checked with the current value before incrementing it. Now, in the loop, we can simply increment our counter, and then return the length. I don't know about you, but that's a lot simpler to understand than the for statement. Even if it doesn't seem that simple to you at first glance, it's helpful to consider the different ways of solving the same problem to appreciate different techniques, their strengths, and their weaknesses. Let's give our string length function a few examples to chew on. And let's see what the compiler has to say. Great. And there we go. 11 characters in Hello World, as before. 0 characters in an empty string. And 3 characters in hi with an exclamation mark. In this example, I want to show you another powerful technique which involves pointers to pointers. I should point out that just as you can have pointers to addresses, pointers to other variables, so you can have pointers to, well, pointers. That's right, you can have one pointer pointing to another pointer, which itself points to an address in memory. Here's a value, a variable holding a value, and here's a pointer pointing to it. And here's another pointer pointing to the first pointer. A pointer to an integer. When you dereference this pointer, you get back the original pointer or address, not the underlying value. You can then use the resulting pointer, dereference it, and you're finally at the value. What use is that? Well, sometimes you need a bit more indirection, a little abstraction if you will. One example is when you need to return a pointer from a function. In the previous example, we returned a pointer to the largest value in a range as the return value from a function. But what if you're already using the return value for something else, perhaps an error code? Then you can do the same thing as what's commonly called an out parameter. Let's write a function to return both the min and max, the largest and smallest number in a set. So we begin with an half-open range defined by the begin and end pointers. These are the in or input parameters. Then the smallest and largest are out or output parameters. They're pointers to pointers, so that we can essentially pass the address of some pointers to this function that the function can then fill in for us, so that we can then retrieve them when the function is done its job. And let's write a simple main function to drive it. And there are some values. And the number of elements in the array. Some pointers that the function will fill in for us. And the function call itself. Now it's very important to realize that the smallest and largest pointers here, these pointers are just regular pointers to integers. They're not currently pointing to anything, but they're not pointers to pointers. They're just plain pointers. The pointer to pointer exists here, in the signature to the min-max function. We satisfy the signature by passing the pointers by the addresses here, providing the address of each pointer to the function. Finally, let's print out the results. Right, so long as that's clear, we can carry on. Implementing min-max is actually quite straightforward, but good practice as you learn C and C++ style pointers. Again, when pointers are involved, it's a good idea to provide a little safety for the caller. If the range is empty, we should simply set the out parameters to 0. 0 addresses, null pointers, just to keep an unwitting caller from overlooking the mistake he or she is making. Now our main function sets the pointers to null before calling this function, but it's common for developers not to initialize out parameters on the assumption that the function will do so. Here we're covering these callers with some grace in the name of security. But that grace only goes so far. Notice what we're not doing. We're not checking whether we actually have valid pointers to begin with. Begin, end, smallest, largest. Any one of these, or all of them, could be an invalid, a null pointer on entry to this function. But we're assuming they're valid. But don't worry. This is not something the caller could accidentally ignore, since the program would crash if we tried to dereference a null pointer. Right, so now with the nominal path. First, we'll give our out parameters something to point to. We assume the first element is both the largest and smallest, and then check subsequent elements, updating as necessary. Notice how I'm skipping over the first element this time. The last time we had a similar loop, we had to still consider the first element since we needed to print out each element's value. But here, we're only looking for the minimum and maximum values, and if it's the first element, then we're all set. So we can use the pre-increment operator to ensure that the condition begins with the next element, if any. Within the while loop's body, we need to just check the value that the current or begin pointer points to against the value that each respective pointer to pointer points to. Notice the double dereference. The first gets to the underlying pointer. The next gets to the underlying value that the second pointer points to. Again, we're comparing values, but only updating pointers. And then the same thing for the maximum value. Okay, let's give it a try. Let's bring up our values. And sure enough, the minimum value in the array or set was 2, while the maximum value was 6. Well, this is undoubtedly the longest module so far in this course. Arrays and pointers can be a challenging concept in the C programming language, but it's also a very powerful concept to grasp and exploit. Without a firm grasp of memory, addresses, and pointers, you'll never really understand how C and C++ works. One of the things that come to light as you explore pointers is their relationship to arrays. Pointers absolutely love arrays. Without pointers, arrays are very limited. We need pointers to unlock various interesting techniques with ranges, as we explored with various examples in this module. Pointers are also necessary in order to pass arrays to functions, since arrays don't carry size information beyond the local declaration. And we covered string literals, a special form of array, an array of characters, with an automatically added null terminator. Finally, we considered some practical uses of pointers to pointers, an essential technique in some scenarios. If you want to move ahead and study the Microsoft Component Object Model, you'll want to make sure you have a firm grasp of this concept. Be sure to check out my course, The Essentials of COM, here on Pluralsight.